Hey everyone, welcome to Zero Labs. Today is Friday, February 27, 2016. I'm Mark Brash, your host, and my very special guest today, Robert Murray Smith. So Robert is waiting in the wings as I speak. For those of you who are not familiar with Robert Murray Smith and his work, Robert is a world-respected expert on graphene, the wonder material of the last few years. Robert is experimenting with and is going into production with a product that incorporates graphene into what he calls the EESD, or electrical energy storage device, because it is orders of magnitude more energy dense than probably the best supercapacitor you've ever seen in your life. And he is working for Edison Electric, and he also is working in conjunction with SunVault. So without any further ado, my very special guest, Robert Murray Smith. And let me apologize in advance. This intro had to be re-recorded because when I did it the first time, I forgot to hit the record button. So I missed the first few minutes of the live broadcast, and basically what you missed was the intro and a portion of the very first question that was asked of Robert Murray Smith. How much does the EESD cost? And he goes into describing the cost benefits of the EESD compared to a lead-acid battery. Also, let me apologize in advance. I did have audio issues. After replaying the video, I discovered that the echo that people were complaining about in the chat room was a result of my wireless microphone that you can see right here. Yeah. Picking up the speakers that are on my shelf over my head up there and going back out over the air. There was no echo in our context or in our chat back and forth with each other, but unfortunately the echo did get recorded for the live stream. That won't happen again. The next time I will wear headphones, I promise. So without any further ado, Robert Murray Smith.
When the production process is ironed out, and we'll be producing these things in millions of units, so you're probably talking a few cents. I'd expect it to drop lower than about $70 a kilowatt hour, something like that. $70 a kilowatt hour brings it into sort of lead acid kind of price range. One of the big reasons lead acid continues to live is because the price per kilowatt hour is so low. So in lots of circumstances, you don't want a really expensive power pack. You don't mind about weight, you don't mind about volume, but you do mind about price. So having a small, compact power pack that can come under lead acid is a real game changer. And that's certainly our target, to bring it under lead acid. It's certainly not there yet, but that's mostly because of the way we produce it at the moment. We're not producing it in millions of units. The whole aim of this has been to make it a simple, affordable process, which is why we've gone for something like using a print methodology, because it's so cheap to produce it that way. We can make tons and tons of these things for next to nothing. That's the whole point of it. Now, I obviously have a lot of competing interests, a lot of different things that I have to do, and that can end up to be a certain extent a time thief. There's things that I have to do in order to address the EESDs on one side of things that stops me working on the production line side of things. So that at the moment, the print machine is actually running, yet I've yet to actually print something because I've yet to finalize the ink regulations. So at the moment, I'm still dictating them. If I can get the concentrated work that I need on it, probably only a week or two before we print them off. The problem isn't that, the problem's getting that time to concentrate on it.
Right. Okay. So the printing process itself, are you actually printing the graphene onto your metallic plates, or are you printing the graphene onto a dielectric, or how does that work?
Well, we could do it either way. One of the problems really is getting good contact. I mean, if we calendared them, that is, if we went directly on the plate and put them through two rollers, it would be a calendar process. The physical process of pressing them closer to the metal plate will reduce the internal resistance of the device and make the device perform better. So there's a whole lot of things we can do to make the device perform better, but they have a cost associated with them and a production side associated with them. We made a deliberate decision to just print them, knowing full well that it will make the device worse than it should be. But then you've got a cost-benefit ratio. So you want the device to be as cheap as possible, but to perform with reasonable power density, not with the best power density. So the whole point is that way around. So we can put them on plates and calendar them slightly together. Equally, we can put them on either side of the dielectric, put together the whole cell and put some clamp plate either side to clamp the whole thing together. Either of those options is going to give you a slightly worse device than you could possibly do. But both of them allow for a cheapness of production that means you're going to get a well-performed device. I mean, the devices have been demonstrating on the channel have been deliberately made in inverted commas a poor way. And it should tell you something about the devices. We're not producing these to exact lab standard. We're producing these for demonstration in a way that they would be produced in a commercial way, so you can see what they actually do, not what they theoretically do. So a lot of the presentation stuff we're doing is actual power delivered at the point of use, rather than running it through something like in Princeton, where we would get a theoretical power density out of it. We've done the actual that you can see, because that's what you're buying at the end of the day.
Right. The last videos, the last two videos that you produced, are basically the encapsulated how to go about experimenting with graphene cells. I thought they were great. They, get your feet wet.
In open technology. I mean, we live in a modern world. There are certain things, obviously, I can't tell people because I have to sign agreements, I have to get these produced, I have to work with people who want to make profit. All of that's very reasonable, but it puts restrictions on things. But even so, I still believe in open technology, and the baseline information is certainly there. And I think that particularly these devices, and remember these can be turned into solar cells quite easily, these devices, solar cells, thermal generators, all of that kind of thing is well within the capability of the average home experimenter to work with and to develop themselves. And I believe that, which is why I do the kind of videos that I do, because I want to encourage that.
Well, you're certainly very good at doing that. I have a couple of technical questions for you myself about the graphene cells. I don't know if you'll be able to answer them without violating your NDAs, but we'll ask the purpose. In your last demonstration, you showed how you apply graphene, or not graphene, graphite to the plate of the metallic plates on both sides of a dielectric, a liquid dielectric soaked in a tissue, right? And you explained that the purpose of the graphite was to increase the surface area because the name of the game is surface area.
About the last video that I did.
I'm sorry?
We're talking about the last video that I did. I had to build a supercapacitor.
Correct.
Yeah, I did two there. One was a carbon material that was activated carbon. But the other was graphene. It was graphene oxide, actually.
Oh, okay. All right. And the object of the game is, according to you, to increase the available surface area exposed to the dielectric material in between the two plates. I kind of wonder why you continue to use a fluid type of dielectric material between the graphene plates, as opposed to using a solid dielectric with the graphene, say, applied to both sides of the dielectric material instead, where some of the graphene actually commingles with the molecules at the surface of the dielectric material itself to increase the exposed surface area inside the dielectric material, and you make a better contact to the backside of the graphene just with the metallic plates because of the very good conducting nature of graphene itself.
Mm-hmm. But it's simple, really. It's just a friction machine. As much
Yeah.
as you handle liquids. And when we make a gel, we have to apply a gel. In order to apply a gel, you need a machine to do it. Machines are capitally expensive. In order to apply a liquid electrolyte after the battery's been encased, you need a guy with water in it. So it's just a really simple thing. But it does, these kind of decisions you have to make all of the time. I mean, when you're researching something, you're doing really two things. One thing is to look at the perfect performance. What's the best you can make? How would you possibly do it to get the top-end performance out of it? And that's great, and it does tell you an awful lot. I do that alongside other people as well. But then there's another aspect to it, and that's the aspect of usability. Getting out there, getting it made. And when you do that, you have to get the best performance you can, but bearing in mind what's going to be the cheapest way of actually producing it. And those kind of decisions change the way that you have to experiment, to change what you're actually looking at and what you're doing. So the application of the liquid electrolyte it is really good. I mean, it's mobile ions, where gel electrolyte have a reduced mobility. So they have great more mobility, and it does need to give you a reasonable product. Perhaps not the best, but that's not really the point of that side of things. If you want to look at getting the best supercapacitor, then a lot of the things that we're doing are probably not very good. And the reason they're not very good is, as you said, you're not getting particularly good contact between the conductive substrate and the active material that you're putting down. You need to improve the contact there. Like you say, perhaps you're not getting the best contact between the electrolyte and the active material surface either. Perhaps not. So you're making decisions all the way along the line when you do these things. And they're not simple problems, they're complex problems, because they're a complex system that interacts in a way that when you put it together, to be honest, you don't really know. So what you do is you put the thing together and stop it at various stages, and then you might do some XRD, or you might do a Raman, try and find out what reaction products you've got. You do that in a series of stages, a series of charge-discharge, so you can analyze what's happening. So perhaps if you've got an asymmetric capacity and you're using something like manganese dioxide, are you getting non-reversible reactions there that are happening? Can you reduce those non-reversible reactions by putting additives in, and so on and so on. It's a long process, and it's a complex process, and it's too complex to try and deal with everything. You have to take your stance and take your bites at that elephant burger and look away at those, really. So, but as I say, my decision points really do with cost, production capability, accessibility, safety, and recyclability. And those are the kind of key issues that I'm dealing with. So, for instance, the materials that I use are absolutely recyclable, that they have no harmful effects on the environment whatsoever. Now, that of course is intensely limiting, because it means I can't use some of the higher order solvents that have been used, things like ethylene dicarbonate, that kind of thing. I can't use those kind of volatile solvents because they go against a couple of the USPs that have actually targeted to be important in the device that we're creating. So you make those decisions for one reason or another. It limits you to a degree, and you work within those limitations. It doesn't mean that if you remove those constraints, you remove limitations, you merely replace them with a whole other set of limitations that you then find yourself working with. So say, for instance, we want to use something quite toxic. Then that can be very frightening to a lot of people. They will make a device that perhaps would perform better, but would be relatively useless in that you couldn't sell it, you couldn't use it, you couldn't ship it, this kind of things. So you get a whole set of different limitations depending on the choices that you make. It's really just choices I've made, and how those choices introduce limitations that I have to work within.
Okay. All right, I guess that sort of actually addresses a couple of the other questions that I had. I was more or less looking at experimenting with a solid dielectric and applying the graphene to it and allowing the solvent in the graphene, or the solvent of the graphene to react with the surface of the dielectric material. And with a solid dielectric, I would think that I could get a higher breakdown voltage than you get with some of the liquid dielectrics that you've been using.
Yeah, certainly. I mean, if you're thinking about things like Lithicon and Nasicon, for instance, which are solid lithium and sodium ion transport dielectrics, brilliant things, hugely expensive, work fantastic. But just fits into that limitations thing again.
Right.
NAFTA, for instance, which is say you want to make a supercapacitor that has two different sides of the cell, so using one set of, you see, the problem is these aren't just capacitors, just batteries. They're capacitors with redox activity to a degree. They've had other forms of activity as well. So I think more or less 6 methods that you can use to store energy within a device. So DLC, insertion, deinsertion, intercalation, deintercalation, Zwitteran formation, bond rotation. All these things you can use within your electrolyte, within your active material. Sometimes you'll get one set of chemicals that behave in one way, sometimes you get another set. You might want to keep those two apart. You use something like an Nafion membrane, which is porous to protons and nothing else. So you can use something like that. But Nafion is something like, I forget what, figure out of the air, about $100 a square meter. Very expensive stuff if you want to try experimenting with that. Does a good job, but it's really, really expensive.
Right. So that obviously wouldn't work in a mass-produced commercial application.
And not so successfully. And it's like I said before, when you're experimenting with stuff, you just don't look at the performance behavior of the device in itself. That's not enough to look. If you want to commercialize, if you want this to be used by a lot of people, you have to think about other things too. You have to make decisions about it, where you want it to go. So say, for instance, we want to produce something for military use, where expense wouldn't matter, but power density would. Then it becomes perfectly viable within that selection set. And there's no reason not to do it, but you have to think about what you're targeting before you begin to target it. So you're hoping to do something for the mass market. No, you wouldn't be using that. You're hoping to do something for NASA or the military. Why not? Perfectly reasonable. Doesn't matter if your cell costs $3,000–4,000 to sell. That kind of thing will find a market in a very restrictive sense. But just a decision I made. So
that is one of the questions that I saw come through the chat room already. Have you been developing any of your products along in parallel with your consumer products for military?
Yes.
I'm sorry, I didn't catch.
Yes, I have. Yes.
Oh, okay. And that's all.
Yes, it is.
Okay. Fair enough. I can't help.
Let's say high-end use.
Okay.
So yes, for things like space exploration and high-end use batteries, yes.
Okay. I can't help but think about a video that you put out, that you were addressing a question that was sent to you by Stefan Haraburton, where you etched your foil. Is that part of your process also?
On this particular process, in some parts yes, and some parts no. Again, you've got to remember that there is no one answer. So very often people ask, what's the best this, what's the best that? There is no one answer, because it's a complex system. It's best fitted to one circumstance or best fitted to another. Now, in terms of a commercial product, would I etch the foil? Probably not. The reason, it's a process and it requires process costs. It doesn't add that much more to the energy density to do it. It adds a significant amount, but also adds a significant amount of cost. So is it appropriate? Not really in my estimation for a mass market product, no, because the cost is just too great for the benefit it would have introduced. It does give you a whole range of devices, okay, because there's a whole range of applications that they're suitable for, but there's never a best answer for something. There's only appropriate answers.
Right. One of the things that I noticed is that, when you were demonstrating the application of the graphene to the metallic foil, is that it comes off rather easily. It doesn't take a whole lot of effort to get the graphene off. How does that then hold up in a product over time when you apply it? What is it that prevents the graphene from disassociating with the metal that you've layered it on top of?
Well, in itself, graphene isn't actually soluble. It's dispersible, but it's not soluble. It'll form a colloid, but it won't form a solvent. So it would just sit where you put it unless you rub it. If you don't rub it hard, it's going nowhere. It won't actually react and dissolve. You can put binders in there to bind it, and there are different kinds of binders that you can use. So some are non-conductive binders, things like PVDF, PTFE. We all know they're insulators, but they're also very good binders, so they do hold it. You don't put much binder in, it's usually about 5 or 10%, somewhere about there. It reaches a percolation threshold. There's enough binder in there to hold everything down, but not enough to interfere too much. Again, it's a trade-off that you're making. There are conductive binders that you can use, but again, they're really, really expensive. So you would only use those in a high-end product. You wouldn't use those in a generic product. You can use just about anything for a binder. A load of things work. But wallpaper paste works really, really well. That's EMC, carboxymethyl cellulose. About 5% of wallpaper paste by weight within your mix will actually hold it reasonably firmly onto something. You're not looking for the kind of hold that you might need if you were making a building, because you're not going to be moving it. Once it's put it in its case and it's all wrapped up in seal, it never moves. It only has to sit there and resist fairly delicate conditions on the whole. There's nothing really harsh that it's going to meet once it's actually encased.
Oops. Okay, let me turn my mic on. I'm trying to toggle my mic on and off because I was getting a lot of complaints in the chat room that there's an echo, and I haven't really isolated where the echo is coming from. I don't know if it's on my end or on your end. They say you should wear a headset. I tell them that you don't like wearing headsets or lapel microphones.
I'm actually using a pretty expensive microphone. It's a Zoom H2N.
Oh,
so
wow.
It's actually really quite a good microphone, so it should have reasonable pickup. So I'm not using the computer microphone or a cheap microphone. I'm using quite a good one because of the show. I didn't want kind of reverb and echo from it. So I don't know myself. I've set it on the XY position, so it's picking up predominantly from me.
Right, okay. Do you have maybe your speakers turned up on your end so that you're getting like an echo from your own speakers? I don't hear it on my end. It sounds perfect on my end.
I might be, because obviously I have to have the speakers on so that I can hear.
Okay.
So
all right. That might be the problem. For the experimenters out there, you've presented a number of different ways to make graphene. There's a whole bunch of different ways to get from point A to point B. In the end, what you end up with is a colloid in a solvent that you use to deposit on your plates, so that you can layer them on your plates very easily. But one of the questions that I had was, if you're taking something like a 325 mesh graphite and you're sonicating it directly to a state of graphene in a co-solvent like acetone water, or like the other co-solvent that you mentioned that I can't seem to find locally here in the United States, is there any benefit to intercalating the graphene first and exfoliating it and then sonicating it? Or is it just a matter of time that it takes to get from point A to point B if you sonicate it directly?
Well, if you intercalate it, you're going to force the graphene platelets further apart. When you intercalate graphite and you have a graphene layer, intercalate graphene, that's called a stage 1 intercalation. When you have graphene, interconnect, graphene, graphene, interconnect, graphene, graphene. So you've got 2, that's a stage 2. If you have 5 layers, it's a stage 5. So if you interconnect anywhere between the stage 1 and stage 5, and then sonicate, because it's shoved everything that much further apart, you're going to leave less sonication energy to actually split it apart. So you can control the number of layers to a degree by the degree of intercalation that you put into something like that. So there can be benefits on doing it, and there's several successful methods for doing exactly that. But it does lead you to a problem of doing the intercalation first. And that can be quite difficult, and for a number of people quite scary, because intercalation requires some relatively difficult chemical processes that the beginner, the person who's new to it, has no experience of. And although I don't do much on health and safety, I have a kind of belief of learning by doing. You still acquire experience by doing, and if you have no experience whatsoever, it's probably not a good idea you're handling concentrated acids in a heated bath. That's probably contraindicated. Probably not a good thing. So if somebody's new to this, then they really shouldn't be trying to intercalate first. But they still want a product, and they still want to play with graphene, so sonicate it longer. Just split up the platelets, break them up, and make them smaller than the original size that they were, but they'll still get something out of it that they can play with. Somebody who's got an awful lot more experience should, yes, definitely do intercalation first and then sonication. It's to do with the degree of experience a particular viewer has got. And if you don't have any experience at all with some of these processes, your best bet is to develop some experience, learn how to handle these materials, and then move on to do those kind of things. Because a lot of people want to get in there and give it a go, so I provide that solution as well, that you can just get in there and give it a go. The other thing to bear in mind is, remember I said that there's no such thing as the best energy storage device. Equally, there's no such thing as the best method for producing graphene. There are a lot of different methods for producing it, and all have their own little quirks. So flat plates of graphene aren't actually very good for a supercapacitor. What you want is wrinkled up plates of graphene. Because when those wrinkled up plates are laid down again, they lay down wrinkled up and give little holes and little channels that the electrolyte can get into. So perfectly flat, lovely plates of graphene are actually next to useless for supercapacitor application. Fantastic for things like transparent printed screens and transistors, that sort of stuff. Brilliant. Rubbish for things like supercapacitors and batteries. So different graphene methods of production are important, really, depending on what you actually want to do with the day. So there is no best method, really. The real answer is to give a few a go, have a practice with it, learn, experiment, and see what works in the application that you want to use it in.
And that really is the key.
Mm-hmm.
Build and learn.
Yes.
Right.
I mean, I actually work for Edison. Edison Labs is the main people that I have an association with, and they have a link to Sunvolt. But I also have a link to Sunvolt, but really the real link is through Edison. And the Edison philosophy is get it, see it. So me and Steve, we're on the bullet with plastic. We were looking at the thermoplastic side of it, how to make it good when we put an injection molding machine. And we were chatting about it, and Steve was saying, look, what about this? Let me turn to the research papers, we'll have a look. And we spent about half a day looking at this. I looked over and said, Steve, why don't we just go and do it? And in 5 minutes we had solved the problem. Because we, in our modern way of approaching things, want to study everything to death. But very often, if you ask yourself that question, 5 minutes in the lab will answer it, whereas 3 years in the line you want. And this is very often what I tell people. Get up and do it, and you can so often answer your own questions for yourself in about 5 minutes flat. Whereas you can have a conversation and an email exchange can last weeks and still not answer the question. 5 minutes in the labs will answer it for you. So I'm a very practical-oriented chemist, and Edison believes in that. Get up and do it, and so do I.
Okay. Speaking of Edison, how's the kit car coming along?
It's coming along. Unfortunately, we've hit a little bit of a blind with that, in that there's a disagreement with the builders, so it's sitting there while we resolve that disagreement.
the best laid plans, right?
That's it. Everything, it's sitting there, everything else is there, but we're having this argument, discussion, let's be kind, having this discussion at the moment.
Right. All right, well, listen, aside from the complaints that I've been getting from the chat room that there's been a lot of echo, and guys, I'm really sorry. I don't understand why. I'll go back and listen to the recording afterwards and see if I can't resolve why I'm getting this echo. I did make some changes to the way sound is routed here, and I'll figure it out, and we'll move on. But unfortunately, you're going to have to just deal with it the way that it is. So I'm going to put this out to the chat room. I'm going to look real quickly to see if I can't find. I know there were a couple of questions that zipped by. Stefan wanted to know, ask him please if he uses the process of the Russian Victor Petrich that he found out how it works to produce good amounts of graphene.
I can't answer that.
Okay.
I use our method for producing good amount of graphene. Yes. How I do it, obviously can't answer.
Okay. That's fine. Let's see. Ask him if he will produce the supercaps himself or if SunVault will manufacture them.
There's no money for me to produce myself. So the beta test stuff I'll produce here. But the idea is to get it into manufacture with a major manufacturing partner. So we're currently in discussion with 3 end companies to do exactly that. But obviously, I mean, you're talking about millions of units, so it's not something I could physically possibly do. It's also something that I'm not really that interested in. I'm not a manufacturer, I'm a researcher. So once I get it to a stage where it's manufactured, that's really my job finished, if you like. I will look at improving it, I'll look at the versions that we're doing and continue to work on those things. But there's an awful lot more things to be doing than setting up factories. It's not something that I'm personally really interested in anyway. So once we've got over the beta test version and the mass market production side of things in place, then I'll pretty much take a step back on that side of things anyway.
Okay. Let's see. Stefan is still pushing. Will he reveal the trick soon?
Cheers, Stefan. I mean, I can tell you this, the information for doing this stuff is all out there. The real key to doing it is just like me. Read, experiment, you'll find it.
Right. And I believe that. What is the maximum charging voltage does he get? Does he get more than 2.7 volts?
In which device? This EESD that we're planning on launching runs at 2.15.
I'm sorry, you broke up on that one. What was that?
Device.
You broke up on that last one. What was that again?
Remember, we talk about Type B devices, with devices with battery-like behavior, Type C devices, which are devices with capacitive-like behavior. So the current commercial Type C device, the one that's been beta tested, runs at 2.15 volts.
2.15. Okay. So then to have a device that is able to store voltage in the range that is more common, then what you would do is stack a number of these devices in series, right, to increase the voltage capacity?
Yeah, so this series parallel. The thing, obviously, is that it's a half CV squared, so you can up the voltage, you can up the density by the square of the voltage, or the voltage difference, so you can get that much more. Your cell is running at 2.75. But there's also another way. You can just increase the area. And because our cells perform so well, we have an enormous amount of slack in that area, so we can store in the same area a greater number of coulombs and a greater number of joules, which is double the power you can get out of it, at the same area than competing devices. So if we take our 1 centimetre device that I went through with you on the supercapacitor follow-up, it basically stores 2 joules at 1 square centimetre, 1 layer. The competing device, which runs at 2.7 volts, is actually 1 centimetre squared times 12 layers, 12 centimetres squared, and that stores 1.84 joules. So a direct power-to-power comparison stores 24 joules in the same package is previously been storing 1.84 joules, even though that's at 2.7 volts and ours is at 2.15 volts. So I actually ran that experiment actually at 1 volt to show you that 1.84 joules was exceeded by our device. So we're looking really at the energy that's stored as opposed to the voltage it can give out, because the voltage it runs at is in electronic terms relatively inconsequential. As you say, you can stack them in series or parallel to make the voltages match as much as you want, really. What you're really interested in is how much power in joules it's got on there, what it can deliver.
Okay. How big will the 1 million farad cap be? And if I'm not mistaken, it's the one that you showed is about the size of a ream of paper.
It'd be about a quarter that size. That ream of paper was actually about 6 million farads.
6 million farad?
Yes. So it'd be about 1/6 the thickness of that. So about that thick.
Yeah.
So it'll be about that square.
Mm-hmm.
By about that. Something like that. That would be 1 million farads. The one I showed you was 6 million farads.
And you speak of that just so nonchalantly. I want to see you put a wrench across that.
I did in fact weld 2 steel bars accidentally together.
Whoops.
That was a whoops. I didn't read my YouTube this week by showing the mistakes to make.
Have you ever considered producing a blooper reel?
I should do, hey? Because one of the problems, obviously, particularly with the 2 showed you how to make, it looks so easy. I mean, it is easy, but it looks so easy. But like I say, I've made thousands of these things. You know, my bin gets full of scraps of these things. So many of them. But I think it would be kind of cool every now and then to do a when things go wrong video. Because they go wrong far often than people know.
Let's see. May you please ask Robert what his Type B EESDs specific power and energy densities are?
Specific power and energy densities?
Yeah.
So per kilogram and per loop? Without referring to sheet, I don't.
Okay. Let's see. Just a comment. I have an idea about embedded capacitors in a flywheel, so I watch Robert's research closely because I believe in what he is doing, and I think this technology together would be brilliant. Okay. I'm not sure where he's going with that.
No, I think I know what he means, actually. He's looking at a variable capacitor as an electron pump. So if you use a variable capacitor where you have basically 2 discs rotating, and you have a metal foil on one disc, take up half the disc, a metal foil covering the other half disc, then the capacitance will vary as the 2 discs pass over each other, reading the full capacitance of that device when the 2 discs completely overlap. Well, that can be used as an electron pump. And it's kind of a cool device. I mean, obviously it requires energy input because you have to thin the discs. But when you do that, then you will actually get a device outputs. Now, the use of that, if you have 2 of those that you don't spin, so you just have them free sliding over each other, and you put them in shoes, that your movement will make them slide over each other and actually pump electricity. So you could put them into your shoes or your clothes, to use them as a kinetic energy recovery device. So it's actually a good idea.
Okay. All right. We have a comment. I think hydrogen cells will surpass the use of supercaps, making all of this research second best. Oh God! What a buzzkill.
Confuse things a little bit. Because supercaps, remember, aren't energy generation devices, whereas hydrogen cells are. Now, there'll always be a need for storing energy, which is what supercaps do. They store energy. At least because the demand for energy use has offset against the energy that's generated. So a fuel cell, hydrogen cell, will generate energy constantly, but you don't use it constantly. So if you're not using it, the energy it generates as it burns away is just going to be lost. So you store it. Then when you need it, you don't draw it directly from the fuel cell, you draw it from your storage. So that kind of load leveling is actually where supercapacitors have their greatest use.
Right, so they could work together.
Anything that doesn't need load leveling in terms of energy generation, so solar cells, wind cells, hydrogen cells, all need load leveling. So fuel cells, hydrogen cells are not going to render it moot as an area of research. Actually, we're just going to thrust it more forward into prominence because it's still going to be needed. Remember, EESDs don't generate, they store.
Right. Right. ZRTYI monitoring YouTube chat. There are some questions there. Okay, let's look at the YouTube chat here, see if I can find anything. Guys, I'm really not monitoring the YouTube chat very much. I'll scroll back a little bit here. Can Robert discuss how the battery works with the hydrogen system in the Edison car?
No.
There you go. Robert has written several books on graphene.
There are people who worry about some strange things. When the bolt first came out, it had a really poor range. Because GM actually did a study on what the average range of the driver was. Turns out it's 38 miles. Most of us drive no more than 38 miles a day. In which case, having a huge range is not really a problem. But people suffer from range anxiety, and they suffer this because they're used to a certain way of behaving. That is, every once to have much petrol you use, you go down the petrol station, you put all that energy into your car about 5 minutes flat and use it the rest of the week. And that's how we're using it. You don't have to think about it. And we think that electric cars have to have the same kind of qualities. Actually, they don't. Most of us use our car to drive to the shops. It sits outside our house, we drive to work, it sits outside the work, it does on average 38 miles a day. If you're a power pack to run that 38 miles a day, most of the time, 90% of the time, it's going to be fine. There's a few people, there are a few times when you do more than that, and we seem to think that we have to be able to do more than that. So we have this idea in our heads that we have to be able to do somewhere about 400 kilometers before a recharge. We don't, there are just sometimes that we need to do that. And that introduces an idea we call range anxiety. Everybody thinks, oh my God, we've got to do this! And so we have this that we have to overcome. So the fuel cell really will probably never get wrong, or run only 5 or 10% of the time, because it really ameliorates range anxiety as opposed to being useful in itself. The main operating system of the car will actually be the storage devices. Every now and then you might have to turn it over to the fuel cell because of your range anxiety, but most of the time it'll just never get used.
Right, right.
Yeah,
and you
we call them the load fairies. But those people who think that your device has to be super, super small and have a huge amount of energy density, they're called load fairies because they don't. Because you have to think about the appropriateness. When somebody is running a wind farm, for instance, on 80 acres of ground, they don't really care. If they set aside a building for lead acid, they're really interested in how much it costs, not how big the device is. So having a load fairy tell you it's got to be like that is not really appropriate if that costs too much. So these things really require a balanced view about what it is you're actually doing.
All right. Let's see. How safe will the battery be if it's punctured in an accident of the supercapacitor?
Oh, it's made out of water, so you can drill it if you like, you can do anything, it doesn't do anything. If you put it on overcharge at the moment, that's one of the things I'm working at the moment, actually, is temperature profiling the battery. It just goes dry. I did this in one video. If you overcharge it, it dries. To bring it back, you pour some water on. If you over-discharge it, pretty much the same thing happens. It's difficult to describe because nothing really happens.
So there's no danger of a fire or explosion if the battery short circuits?
So,
There's no danger of a fire or explosion if the battery short circuits when it's been punctured?
yeah, but not in the battery, in the cable that you're short-circuiting with. That'll burn. So
Right.
if you attach a cable to a positive and negative, the PVC will burn off. The battery thing will happen. If you stab it, it'll leak, but it'll leak water. And if you handle salts, nothing will happen.
Okay.
It's a bit boring.
Well, when you consider, how everybody got in an uproar when a Tesla Model S got into an accident and caught fire, and then you compare that against the statistics for gasoline-powered automobiles that catch fire on the side of the highway, but everybody seems to forget about all those that you drive, right?
And this, I find this hilarious because obviously, I'll do something, and I've been working with, salt water or sugar water, and I get people telling me to wear glasses and gloves. And I think that every day they get on a high-powered explosive, rush around at stupid speed. Some people smoke while they're doing it, but periodically set it alight, and they think it's fine. They're just seeing But they have this enormous flammable liquid coming out of the hose that they just stick into a pipe and have a look at. It's strange sometimes.
Ask Robert if graphene has
The anxiety. But it's to do with the electrolyte that's being used. These are organic electrons, and they're high density to each other, very close proximity to reactive components. So this is another reason we've chosen to go with an aqueous system. It's 100% safe. There's just nothing that will happen. It will put itself out. Whereas if you use something like an organic electrolyte, yes, it's going to burn. And we could use organic electrolytes in our EESDs, and they probably would be an explosion hazard because they're the same kind of thing. Reactive materials in petrol, basically. But we don't. We use water. And the use of water means they're just amazingly safe.
Wow. Ask Robert if graphene has promise in seawater heat exchangers. That was my expression too.
If you're thinking about the experiments that have been run off of Chennai at the moment, then yes, it does.
Okay.
There is temperature differences between the top layer and the bottom layer of the water to run desalination plants, and they use that in the Peltier devices at the moment to generate the electricity needed to desalinate. There's a big experiment running off the coast of Chennai at the moment with that. Because graphene has potential there, yes.
Okay. Someone in my chat room was kind enough to transcribe a question from the YouTube chat. How much will these caps cost when it gets... Well, we've already answered that question.
I think we know that.
Yeah. So you said the end cost will be similar to lead acid in the end. But of course, we're not there yet. Fire with lithium-ion batteries is a hot topic right now. Does he have any idea how the orbo electrets work and what layers they might use? Just the carnauba wax? Have you heard of the Storn Orbo power device?
I've heard of it. I don't really know much about it, to be honest.
Yeah. Okay.
And I thought it was the same one I'm thinking about. I thought it was an unusual dielectric they were using, and it was basically a flat plate capacitor, but they had a particularly strong dielectric, so they could put a huge voltage on it.
Okay.
That's memory, but I may be wrong.
Right. And let's see. Any plans to continue research with?
One I'm just describing is a copper calcium titanate, I think, is what they're using. It's the K value of sort of 2 million or something stupid.
Okay. Can you ask Robert if he has any plans to continue research with Testatica? I don't even know what that is.
True, but it's like a lot of these things. It takes time, and I have to prioritize the time because it's basically just me. So there are lots and lots of promising technologies. I work with the things that I think are the most promise at the moment. So in order of business, we're probably looking at the EESDs, the graphene reinforced plastic, the thermocell, then solid-base solar cells. We'll be looking at after that. Then we might get back to that sort of stuff. Although we do have some stuff to do with the switched magnetic luxance motor that's generated a lot of interest, not within the YouTube, but within the engineering community.
So you mean you don't have infinite amounts of time to devote to all of the projects that people come to you with?
Isn't that strange? I waste 2 hours a day sleeping.
Right? All right. Well, listen, sir. You've been very gracious being my guest on the Zero Fossil Fuel Show. Do you have any closing comments that you'd like to make before I let you go and enjoy the rest of your evening?
I'm just doing some charge-discharge tests. I'm just about to go back down and carry on with them. It's a pleasure. Thank you very much for having me, and I hope I've answered some of the questions people have had.
All right. And that's it. I've cut Robert Murray Smith loose for the evening. Robert, I really want to thank you for being my guest tonight. I will go back and look at the recordings. Hopefully, I can figure out why we got all this echo that people were complaining about. Thank you all for joining me. I hope you'll join me on my next live broadcast. I'm not sure who the guest will be. I've asked Stefan Harlberton if he wants to be my guest from overunity.com. He said yes. I'll see if I can work out a date to get him in here and have some more fun with these live broadcasts. Thank you all for watching. As always, please rate, share, comment, and subscribe to my videos. And peace, everyone.